Okay, so yeah, let's start this afternoon's talk. So we are here from Professor Mok from University of Hong Kong, who will talk about the rescaling method on subvarieties of bounded symmetric domains arising from their quotients with respect to co-compact lattice. Okay, let's welcome.
Okay. So I'd like to thank the organizers for their kind invitation. I am a complex analyst and then turned complex differential geometer. So basically, it comes from complex differential geometry today. But I was, however, motivated to study this problem from problems arising from arithmetic. And then also found other applications of it. So let me start. So in Riemannian geometry, you study isometries, and it's an equation. It's a system of equations. It's a matrix, equality of two matrices of matrix-valued functions. So it's a big system. When you turn to Hermitian manifolds, the only difference is that you use Hermitian matrix instead of a Riemannian matrix. So the equations are basically the same. So for each pair of indices ij, you will have one equation. Can you see the dot? Okay. So now when it comes to a Kähler manifold, the difference is that for a Kähler manifold, there are local potentials. So when you say that two metrics are the same, it almost says that the potentials are the same, except that the potentials are not unique. You can have two different local potentials differing by the real part of a holomorphic function. Okay, so this is putting down the more precise term. It says that the difference between the two functions, two potential functions, is the real part of a holomorphic function. This certainly is the case locally. You restrict to a ball. Okay. Now, let's now specialize in the case where the metric is a real analytic metric. In other words, you can write down the potential as a real analytic function, emitting therefore a power series expansion. So the function is written this function phi here. So this is common in complex analysis. When you have a function that's real analytic, you can introduce an auxiliary holomorphic variable or set of variables, which is the W here. So the W here. And so the function phi z, small phi z, is simply big phi z, z. So the function big phi is then holomorphic in z and anti-holomorphic in W, like the Bergman kernel. Now, in 1953, Calabi defined the notion of a diastasis. So this is a big invention. It's sort of normalized the potential function. Now, here is what it is. You take this capital phi, and then you define, for a pair of points nearby, the delta m is the manifold xy, to be this expression. So I don't think the pointer, I can't see the point. So, but phi xx minus phi xy and so on. Now, if you compare two potentials, you have a phi and a phi prime, then the difference is given by this h. H is small hx being a holomorphic function plus small hy bar. And now you compare the two functions, delta m and delta m prime, arising from these two potentials. The difference would be very simple to write down. It's simply equal to 0. And therefore, you may say that actually you have a normalized potential, and then when you have an isometry, the diastasis would stay the same. So then in the same paper, so there is the work of Calabi, which says that when you have holomorphic isometric embedding of a germ of holomorphic function of Kähler manifold with real analytic metric into the projective space, then it is possible to analytically continue it provided that the image does not lie on any hyperplane. But you can analytically continue it, and provided that f does not lie on any hyperplane, then f is uniquely determined up to a projective unitary transformation. The idea is that there is some set of functions called the resolvents, and then the rank of the resolvent is something that you can work with in order to prove analytic continuation. That is, the property of being able to embed into projective space is an analytic property expressed in terms of vanishing of certain functions. Okay, now then he also gave a condition under which the extension would be single valued. And this is the case when you have global potential, for instance, when you have the Bergman metric. Okay, so just a revision on the Bergman kernel. So the Bergman kernel on the bounded domain is given by the square integrable holomorphic functions. You choose some orthonormal basis, any orthonormal basis. And then you can write a kernel, KZW, by this infinite sum. So this is well known. The point, however, is that this function actually does not depend on the choice of orthonormal basis. And this you can show by using the reproducing property. And then you can define the Bergman metric by simply taking log KZZ. So for instance, if you are on the board, it's minus log, you send up to a constant 1 minus absolute value z squared. And then by using Bergman's coordinates, one can show that this is always a metric when you have a bounded domain, because there are lots of holomorphic functions which are bounded, in particular L2, and you can use a good one when you try to compute at one point. So here are the bounded symmetric domains, which are the major objects that will be studied. So the ball is the analog of the disk in high dimensions. Already B2 is not isomorphic to delta square. And then there are 4 series of classic domains classified already by Elie Gardon. Those are the Riemannian symmetric spaces of semi-simple type, or with G-simple in this case, which admit compatible holomorphic structure. And there are 2 exceptional domains. These are the domains of dimension 16 and 27 pertaining to E6 and E7. So now I list the Bergman kernel, the classical ones. The point I want to make is that the Bergman kernels are actually rational functions in Z and W bar. This is even the case when you take the exceptional domain. One can give a uniform proof. One doesn't have to compute it, but of course, in classical cases, you can compute it easily. Okay, then now let me address the question of analytic continuum of holomorphic isometries. I learned to try to treat this problem. So the question is, if I am given a germ of holomorphic isometry, let's say between 2 bounded domains, in particular between 2 bounded symmetric domains, can I analytically extend it? The reason why people were interested in this was actually due to the number theorists and algebraic geometers. Clausel and Ulmo were studying the question of finding correspondences that commute with Hacker correspondences. And by iteration, it turned out that they can reduce the problem to complex geometry. So I was visiting Oxay, and then I got interested in this problem, and then I tried to solve this problem in a general context. Okay, so I should say something about the interior extension. A germ means, let's say, suppose I have a map from a ball into a high rank symmetric domain. Their Bergman kernels are very nice. Now, I have a germ of map which is only defined in a neighborhood of 0. Okay, so now the question, does it extend? I want to say that the extension, Ulmo and Clausel were using Calabi's diastasis. They're looking at the real analytic function, what I wrote as the capital phi. And then they prove interior extension and then prove extension beyond the boundary and so on. And this was essential for their work. It turned out that actually, if you make use of complex analysis in the way that I did, using the polarization, introducing an extra set of variables, polarizing, then actually the interior extension follows from Calabi already. The Calabi says that you can embed, you can extend if it's a map into Pn. And this Pn can be P infinity. This can be P infinity. And so you take a bounded domain, you use an orthonormal basis, and you get it mapped into a P infinity. You compose a map, and you extend it. That implies the extension of the original one. However, if you do this, then you get trouble when going to the boundary. Because in the embedding into P infinity, you completely lost sight of the boundary. The boundary is nowhere. Right? You take a ball and embed it into P infinity, you don't know where the boundary is. Okay, so I gave a solution to this problem from the following point of view. So this is just about extension, how one can make use of Cauchy-Schwarz inequality to prove unique univalence and so on. So that's not the key point. The key point about these domains, bounded symmetric domains, is that they are circular domains. These are the Harish-Chandra realizations. The circular domains has, when you look at the Bergman kernel, they have the action of the circle group. So invariant under the circle group simplifies the problem. So these are the diastasis or polarization of diastasis written as capital Phi ZW. I don't know how to make this work. Okay, so here is how you take a circular domain and you write down the equation on the diastasis. So this is these are the equations. It's important that there's a scaling constant lambda, and this lambda may be a real number. So you have to raise things to the power lambda. So a priori, even if k is rational, this is not a rational equation, or not an algebraic equation because lambda is real. However, when you're on a circular domain, you can extend a little beyond the boundary by shrinking one variable and extending the other variable. And therefore, this implies lambda is rational. The rationality says that this equation would be algebraic provided that k, the two Bergman kernels are algebraic. Okay. So this is the result, the main technical result, which allows me to do analytic continuation beyond the boundary. In fact, one can extend it beyond the boundary so that everything is algebraic, provided that the k, the Bergman kernels are rational functions. The reason for this is the following: you look at these functional equations, polarized functional equations, and so if you put in zeta equal to fz, f is the germ of maps, and this is satisfied. But you may have other zeta for which this is satisfied, so you look at the set of all solutions. And then for each w sufficiently close to the origin, you get an equation. So you have an infinite number of holomorphic identities, and now you consider the common solution set of this infinite family of holomorphic identities. Then you get a certain variety, and this variety contains the graph of the germ of map. And this may or may not identify with the germ because it could be a higher dimension, and this actually happens. So it's easy to cook up examples where this actually happens. So the difficulty is that one has to cut it down so that the dimension matches. And if it matches, then you can say that the germ of the graph agrees with the common zero set of a set of algebraic equations, and that is the algebraic extension. And after having done that, then in various situations you can prove that these are geodesic. And that was the original purpose of Ummo and Kähler. Now, I will just say very briefly how this is done. You look at this set of solutions, and maybe that's not just f, you have ft. So that's a deformation of the common solution, f, which is the germ of map. And then you can look at this identity, and since the right-hand side does not depend on t, and when you differentiate, you would get 0 on the right-hand side. So then you keep on differentiating this, and now you can make use of Bergman kernel, the Bergman coordinates that was used at the time of the invention by Bergman. And you can use that to simplify calculation so that when you first meet a non-zero derivative, so you differentiate k times, when you first see a derivative that actually turns out to be expressible in very simple terms in terms of Bergman coordinates. And it turns out that each point of the graph, the germ of graph, would give you a certain equation, And this equation says that the image of the map must lie in the zero set of some extremal function. And what is an extremal function? An extremal function is, well, as Bergman saw it, is that you maximize the value of an L2 holomorphic function, and then you look at the orthogonal ones, and you maximize derivative in various directions, and so on. So in other words, whatever they are derived from the Bergman kernel. So the extremal function is as good as the Bergman kernels. Therefore, especially in the case of balanced symmetric domain, you would end with the consequence that you can add a number of equations, an infinite number of equations, then you would be able to get the solution. And since these are algebraic equations, what you get finally is the graph is already algebraic. So this is a theorem with a little bit of work. Let me just say what it is. It says that if you assume k omega and kd to be rational, and you assume completeness of the Kähler matrix, then a germ of holomorphic isometry extends to a proper holomorphic isometric embedding. So as good as you can hope for. And in the case of bounded symmetric domains, by additional work, you can prove that these are holomorphic totally geodesic isometry by looking at boundary values, provided it's not the disk. In the case of a disk, the boundary doesn't carry enough geometric structures for you to work on. For instance, when you work on the ball, you can make use of Alexander's theorem. When the boundary is mapped to a boundary, you know that this is an automorphism, so you can have cancellations and so on. So actually, it was a question that was raised by Ulmer and Clausel, whether there exists sort of esoteric holomorphic isometric embedding of a disk into n disk. And they thought that there were none. It turns out that there are, and actually I wrote down a simple one. And here is the statement. If you make use of the upper half plane as the model for the disk, then you can write down an explicit equation by taking the p through it and multiplying by the p through it of -1. So it's like turning the simplest one is take the square root and then multiply by I. So you have two components. And how do you see that as an isometry? I was working to actually prove the conjecture that they posed, and until I finally saw that it's possible perhaps to get a counterexample. And the first example I tried was a counterexample. And the proof is high school trigonometry. So in order to verify that this is an isometry, you look at the potential functions, and the two potential functions must agree, and you translate this into a certain equation. The equation is what you can do in high school, except that you have to see it. Now, for some time again, I was under the impression that it's very difficult to construct a holomorphic isometry of the ball, two ball, for instance, into a bounded symmetric domain, for instance. Until I hit upon an example, and this example turns out to be very important for my later study. So this is a bounded symmetric domain, for instance, just an example is I minus Z bar transpose, Z being positive. So the boundary is semi-algebraic. So it's defined by algebraic inequalities. And then there's a stratification. You take the regular part of the boundary, you take a point, and then this omega is embedded into its dual. For instance, the type 1 domain, this is D1n PQ. Let's say I can pick PQ. It's inside the Grassmannian. So on this Grassmannian, this Grassmannian can be embedded into project space by the Puig embedding. So there are many minimal rational curves, the straight lines on there. You take the straight lines, so then you take straight lines passing. Now, note that an affine line may not be a minimal rational curve. Only certain of them are the minimal rational curve. You just take this set and take the union, and then you intersect omega. What you get would be actually a minimal disk. So you get a union of minimal disks. And the statement is that this union of minimal disk is actually an isometric copy of the p plus 1 dimensional ball. So should I say this? So Well, so it's the general notation. So you can, this symmetric space, you can take it as G mod P, and then take a regular point, and here there's a certain dimension, I call this dimension P. And then this whole thing is P plus 1 dimensional. And then there's one parameter group action which shows you that the geometry of this, this set is the same as the asymptotic geometry. And when it exits the boundary, it's actually strictly slow convex. And you can make use of complex analysis to say that the holomorphic sectional curvature is -2, and therefore it's a ball. It's an isometric copy of ball. You have to show that it's simply connected and so on. So this is an important example for me. Okay. Okay, now I want to say something about, again, in staying within holomorphic isometry, to say something about the holomorphic isometry embedding from the disk into a certain domain. So let's say I take a parasymmetric domain, omega, and suppose I have the theorem that an isometric embedding of the disk is algebraic. Of course, it may also go in other direction. It may leave like this. So it turns out that if the disk actually traverses the regular part, then it is relatively easy to treat it. But if it traverses a corner, then the analysis is quite difficult to carry out. So these are like, so you have intersections of boundaries. So then we proceeded to, well, what we want to prove is this, that this is asymptotically totally geodesic. And that turns out to be applicable to questions in number theory. So, so how do we approach this problem? We approach this problem by proving by contradiction. The point is this. Suppose there exists a counterexample, that at a general point, it is not asymptotically total geodesic. Of course, in the boundary, you have an arc. So I take the general point of the arc. So suppose at a general point of the arc, the second fundamental form has absolute value non-zero. Then I can do what is called the title of this lecture, which is the scaling method. So the geometry looks like a boundary point, so I can renormalize. I can rescale by composing with automorphisms until I get a certain map, which remains a holomorphic isometry, and this you can extract convergence of sequence by Montel theorem, and then you get a holomorphic isometry which behaves like a boundary point. So it would not be difficult to imagine that you can get a homogeneous example. We didn't do that, but it would not be difficult, in fact, to prove it. But we did not need to do this. But first of all, even if you get a homogeneous one, how do you get a counterexample? If you get a homogeneous one, there are homogeneous isometric embedding of the Pn into, well, let's say simplest P into P squared, for instance, is an isometry. So you have Veronese map, you have Sager embeddings, and so on. So you must be able to make use of negative curvature in some way. So we make use of both. So this is how we did it. Okay, this is the rescaling argument. The rescaling argument is this line. You can certainly, by rescaling, obtain another example where all the tangents are equivalent to each other. What do I mean by equivalent to each other? The isotropy group action in a high rank situation is not homogeneous. So then there are normal forms of these tangent vectors. And what one can prove is that you can, by renormalization, get another example where all the tangents are equivalent to each other. And what does that amount to? So let's start do this special case. And finally, the contradiction will be obtained by saying that this special case is good enough. So all cases can be reduced to this special case. Okay, what's a special case? I assume that I have this Z inside omega, so this is Z inside omega. And I assume that this to be a tube domain. So how do you characterize the tube domains? The tube domains are precisely those for which there is a determinant, essentially. So the vanishing of the determinant defines then a hypersurface in the projective tangent space. Therefore, you can draw, so suppose I have this domain omega over here, then you can draw a certain hypersurface living inside the PT omega. So this, I would call this S. Okay, so this S is a hypersurface. It carries a certain homogeneous metric. And this hypersurface, in fact, as a divisor line bundle, is equivalent to something coming from the tautological line bundle. And it carries a certain homogeneous metric. And then you can write this down. So the absolute value is with respect to this homogeneous metric. Since now, so this is defined by S equal to 0. By S equal to 0, it's the vanishing of the determinant. So then suppose now I have a certain curve here. The curve must go outside of this. This is PD omega. And so you have another, well, let me just thicken it. So you have something, this is the lifting of a curve. So it's outside this hypersurface. So the value of S would be a constant, because they are homogeneous. And so you can look at this Poincaré-Long equation. On the left-hand side, this will be identically 0. The right-hand side is expressible in terms of curvature. It actually involves two things, the curvature function and also the second fundamental form. And then it's not surprising to see that you can get something out of there. And you have to make use of negative curvature, of course. The reduction of this to the tube domain case, and this is not just tube domain, you have to have this as maximal rank. Because in the disk in delta R, polydisk of dimension R, there are different geodesics. The maximum one means the diagonal. The reduction is done by it's an integrability problem. So in general, I can insert in some tube domain so that the problem reduces the problem on the tube domain. But this reduction is it's not a simple thing, but it's by making use of techniques that are developed in different complex geometry. It's a non-equidimensional integrability problem. Okay. So now I want to give application, and this was again one of the reasons for studying asymptotic total geodesy. So when I visited Oxford, Clausel was showed me this work of his, and which was done by Lie theory. If you have an equivariant holomorphic map between a bounded symmetric domain, so is it necessarily totally geodesic? Sometimes in our mind, we don't make a distinction between total geodesy and isometry, but they're different. Right? So then he could prove, making use of Lie theory, that this is indeed the case when it's asymptotic, when it is equivariant. However, the argument he used actually failed in the case of exceptional domain. The statements are false in the exceptional domain case. And then I thought about this problem for some time, and I came up with some idea, and then we worked this out. Actually, the asymptotic total geodesy can be made use of to prove this. You can reduce the problem to a case where D is a disk by slicing. And when you have an equivariant map, of course, the norm of the second fundamental form is a constant. If it's asymptotically 0, therefore it must be 0. So this is just the argument for reduction to the case of the unit disk. So here, let me say something about the uniformization theorem. So it was a study of holomorphic isometry, but now this can be made use of to prove some uniformization theorem, which was, again, a problem that I've been dealing with for a long time. So since the generalized Frankel conjecture and so on. So we look at ways of characterizing the universal cover. Okay, so here is the situation where I have a bounded symmetric domain, and I have a certain algebraic subvariety. So the algebraic subvariety, so you have an algebraic subvariety, and on this subvariety, you have a certain quotient by the a certain group of automorphisms. So it goes like this. So suppose I have a bounded symmetric domain, and I have some algebraic subset called that Z. And suppose I have a gamma Z modulo gamma check is equal to Y, and this is projective. So it's uniformized by Z although it might not be simply connected a priori. And the question is whether Z is automatically total geodesic. This is a sort of, in the co-compact case, this is the type of question called bi-algebraicity. The question is, instead of gamma check, you might have some gamma inside automorphism of omega, which is a lattice. And then this gamma check is a subgroup of gamma. So that is a special, this is a special case of the general case I was dealing with. Okay. Okay, so how did we go about proving this? Let me just look at the statement. Okay, so suppose I have gamma check, this is actually the, this is certainly infinite. And since it's algebraic, the subgroup that stabilizes it as a set is algebraic. This algebraic set contains an infinite number of elements. Therefore, there must be some algebraic group acting on this Z. There must be some algebraic group. Now, you make this algebraic group as large as possible, and I call this H0. You can, by the Poincaré embedding, you can complexify it, and that acts on the dual space. Okay. So the statement here is that if you look at this H0, which is non-trivial, you complexify it, then one can show that this Z is actually pseudo-homogeneous under H. Pseudo-homogeneous means that if you make H acting on it, it may go out of it, but it preserves the whole set. Z inside, Z is inside Z check, and this is in. So this is algebraic. So it would, actually you can show that this is, well, this is H acting at a certain point and then intersect with omega. So Z is equal to this, or some irreducible component of this. Suffice it to say that this is a statement that makes use of complex analysis, essentially the Riemann extension theorem for Puris harmonic functions. The main thing you have to prove is that I take this Z, I have to prove that if I take the smallest projective algebraic variety containing it, it would already fill up the space. So essentially, that's what I want to prove. And this one can make use of the maximal principle of a Puris harmonic function. Let me skip it. I'm just putting down. So this is, you have to prove that there does not exist any proper subvariety of Z. So H0, so this is a certain orbit, this is complex, and you have to prove that this cannot be contained in anything proper inside that check. And if you do, then you can, by pushing down to the image, obtain a bounded Puris harmonic function which is non-constant, and that violates maximum principle. That's essentially what it is. Okay, in order to prove my theorem with Chen, an ingredient is Nadel's semi-simplicity theorem. He was studying the automorphism group of the uniformizing manifold of a projective manifold with ample canonical line bundle. And then he proved that this is a semi-simple Lie group without compact factor. Okay, this proof makes use of Kähler Einstein metric. It makes use of stability. So it's not elementary. It makes use of the existence of Kähler Einstein metric. Now, okay, this is just a reduction of a problem. This is an adaptation of Nadel's argument. I'm now looking at this Z and look at its automorphisms. Okay, and I only look at automorphisms that come from automorphisms of the bounded symmetric domain. The proof goes through to prove that this is semi-simple, and that's all I need. I don't need that there are no compact factors. Now, so how does one prove the results of bi-algebraicity of myself and Chen from Nadel's theorem? Well, the point is this. Gamma check is, I have this gamma check here. I have this gamma check here. And I can also consider the quotient of omega by gamma check. Of course, this might have infinite volume, so you can take x gamma check to be omega. Okay, so this might have infinite volume. Okay. Now, so then here you have this variety Z, and it has an automorphism or some restricted automorphism which is semi-simple. So the semi-simple thing has a maximal compact. And then by the center of gravity argument, there's some point which is fixed by the maximal compact of the group. So let's say I already know that this H is some semi-simple thing, and so you look at submaximal compact, and this is fixed by L. And then the semi-simple group will give you then an embedding of a Riemannian symmetric space. Okay. So originally, I have a map of what Y is by definition is Z modulo gamma check. So I have a representation of this as automorphisms of this set. But now I can also represent it on the orbit. So I get another representation of the same fundamental group. You have two fundamental group, two representations, and they are cohomologous to each other, and therefore volume integrals are the same. So then here is the key point. So you have two automorphisms. So this is just putting down words what I already explained. So this is okay. So there are two representations. This is by making use of the maximal compact. This is by looking at Z set, and this is the orbit. The orbit is less at most equal to Z. Right? So you have this inequality, but the integrals agree. The fact that the integrals agree actually means that you have equalities. If the dimensions are different, then you will have on the one side a positive integral, on the other side a zero integral. So it's a cohomological argument. The cohomological argument says that actually this Z is nothing other than this orbit, essentially. And therefore, your semi-simple group is actually of Hermitian type. When it's of Hermitian type, and then by the equivariant theorem, this Hermitian type must be totally geodesically embedded. And therefore, this must be totally geodesic. Proven that this must be totally geodesic. Okay, now there comes to some applications which arise from number theory. So this is the moduli space of elliptic curves. It's just quickly going over some basics. Of course, the first example of complex analytically of a uniformization map is C to C star. This is the exponential map. But then you also have the upper half plane, and you can model out by SL to Z. And this is the J function. Of course, the J function, well, this is not exactly a uniformization because there are fixed points of SL to Z acting on the upper half plane. But of course, you can go to a finite index subgroup. Now, so for tau and tau prime belonging to H, we have S tau isomorphic to S tau prime if and only if tau prime is A tau plus B. So it's acted by SL to Z. So therefore, the set of equivalent classes of elliptic curves is simply given by, well, H modulo S PSL to Z, and this is given by the J function. Okay. So this is standard information about the J function. The J function can be computed from the lattice, or defined by the lattice. And it's a quotient of two modular forms of the same degree. Now then comes some problem that the number theorists were considering. So this is the Andreault conjecture. They were looking at special points. And what is a special point? A special point is a point which is algebraic on the upper half plane, and whose image under the J function is also algebraic. And this goes back to the work of Schneider in transcendental number theory, that this tau must be coming from an imaginary quadratic extension of Q. This is, in fact, a very nice theorem to teach. It's elementary enough. It's a Schwarz lemma, is essentially, and the pigeonhole principle, and it makes use of basic complex analysis, but it has a big implication. This is found in Serge Lang's book on transcendental number theory. Now, then there comes the Andreault conjecture. The Andreault conjecture is the following. It says that if you have an infinite set of special points, so you define the notion of special points for omega mod gamma, when gamma is an arithmetic lattice. Okay. So taking algebraic values both in the domain and target with respect to some standard embedding using modular forms. And the conjecture is that if you have an infinite number of such special points, then its Zariski closure must be what is called a weakly special subvariety. So essentially, a totally geodesic subvariety. They didn't use this language, but it was proven later on by Moonen that actually what they call weakly special subvarieties are exactly the totally geodesic subvariety with respect to the Kähler dimension. And then there came the strategy of Zanier, and which was done in an article by Pierre Zanier, in which they reproved the Ngaiming-Mok conjecture by making use of a certain strategy. The strategy is the following. It's a question in number theory. So it involves algebraic number theory, counting Galois orbits. There's some Galois group acting on points, and you have to count the orbits, estimate the size, and so on. But then, in order to prove the theorem, you have to do certain induction, and you have to go to high dimensions. Now, once you go to high dimensions, there's room for doing geometry. I don't know how to do geometry with single point. Because Fountings could, but in general, it's difficult to do geometry. You have to associate some high dimensional object to a point, then you can do geometry. But you can certainly do geometry with high dimensional varieties. Okay, so then there are two components. The first component is an arithmetic component consisting of lower estimates on the size of Galois orbits of special points. And then there is a geometric component, which is a characterization of Zariski closure of the image of an algebraic set. So the picture would be somewhat like this. You have some algebraic set. So let's now come to a situation where I actually have a lattice. So I have here something which is an X gamma, which is omega mod gamma, and you have this uniformization map, and this is something algebraic. So what I mean by something algebraic is an irreducible component of the intersection of an affine algebraic set with the domain omega. So you look at this, and of course in general it's not closed, but then you take its Zariski closure. Then what is called the Ax-Lindemann-Weierstrass conjecture was that the Zariski closure inside gamma should be totally geodesic set. So this was the second component if you want to solve the underlying conjecture. Okay. Can you say it again? Totally geodesic, yes. Under Bergman or Kähler Einstein is the same. Okay, so let me bring you the terminology by going back to transcendental number theory. So there's the Lindemann-Weierstrass theorem. Lindemann-Weierstrass theorem says that if you take n algebraic numbers which are linearly independent over the rationals, then the exponentials are algebraic independent. So this is a gem. And then there was a conjecture due to a student of Chandrael in the 1960s called Chandrael's conjecture. It says that if you relax the condition Q bar here by just taking complex numbers, and you look at these 2n numbers, then the transcendence degree is conjecturally at least equal to n. And that's the Chandrael conjecture. And Chandrael also made conjectures about function fields. And the function field situation was solved by X. But then these function field analogs can be generalized to Shimura variety. And it turns out that that generalization has a lot of implications in number theory. So let me just say that this is a very hard conjecture. If you just look at a situation where these are algebraic, this is still unknown. And even a special case of this done by Alan Baker was considered a big achievement in this direction. Okay, so the Ax-Lindemann-Weierstrass theorem is to say that this is totally geodesic. How does this relate to transcendental number theory? I will have to explain a little later. So the Ax-Lindemann-Weierstrass theorem was proven after work of Yafayev and then Zimmermann, and finally in an article in 2016, which says that the conjecture is correct for gamma arithmetic lattices. Okay, I was led to consider this problem after Wishoff was lecturing at Hong Kong U. He introduced me to the underdog conjecture, and after some discussion, I saw that my techniques, actually, I was thinking about problem in this direction, actually could be used to attack the Ax-Lindemann-Weierstrass conjecture at that point, but without gamma being arithmetic. So gamma can be any lattice. So in principle, that was how I saw it. And Wishoff was lecturing in 2012. Okay, so this is an article which I published a lot later, but although I was lecturing on this in 2013 in Paris and at ETH in 2013. Okay, so the statement of is simply this: if instead of the general situation of bounded symmetric domain, I just look at the situation of the ball, and I take something algebraic. This is x gamma equal Bn. Gamma is a lattice. It might be the case that you have infinities, whether it's compact or non-compact, doesn't matter. The statement is this: if you take this gamma is just a lattice, it's a lattice, and you look at this image, and you take its triaxial closure, then the pi of this z, triaxial closure is inside x gamma is totally geodesic. So I prove this by a completely different approach. So let me say how actually so a very important ingredient which has been developed over here. So this proof by Klinkler, Olmo, Yafayev makes use of different ingredients. It makes use of Hodge theory, makes use of complex differential geometry and work of Huang To, and also very importantly makes use of what is called O-minimal theory. So this O-minimal geometry found its way into complex geometry, as was already in the conference in Italy, for instance. So there were many different application of this minimal geometry. The basic thing, this comes from model theory, and there are estimates of the size of points with bounded heights, essentially. And this kind of estimates, without being able to explain it here, I explained it last year for the Future of Science Award. So then one can make use of some results due to Kähler and Wilkie in getting bounds of algebraic or rational points on Rn with certain given a priori given bound height, unless you have some subvariety which is algebraic, and this subvariety can contain infinite number of such rational points. So this is basically the setup, and this has a precedent actually in works of Bombieri and Pilla, which is of the nature of Diophantine estimates. So in order to be able to do non-arithmetic situation, I have to completely give up the O-minimal theory, because that's up to this point nobody was able to make that work. So how I did it by looking at foliations. So essentially, you look at, okay, you take the Z. So Z is this element belongs to a certain component of the child scheme, inside the child scheme of Pn. So you form the universal family. So you have this universal family, this going over Pn, and this going over K, and this over Pn. You take this U, and now you can restrict U over the ball. So ball is inside. So you have the ball inside Pn, and you have a U lying over it, and then you can take U restrict to the ball. And then you can now make a gamma working on it. You can make gamma working on it, so you can take a quotient, and you can projectivize, you can compactify it by making use of L2 estimates and so on. So you can work on something which I would denote by U gamma. So U gamma is something that sits inside X gamma, which is Bn mod gamma. And then this guy has a certain foliation. And this foliation then projects to a certain, what should I call it? It's a multifoliation, but you can extract from it. If the side closure is bigger, you pull it back, then you would thicken it. You thicken it, you will have an infinite number of leaves passing through the boundary. And each leaf is algebraic, but the transversal parameter here is only analytic. It is not known to be algebraic. But now that you can make use of the rescaling argument. The rescaling argument says that I have this thickened, because I'm taking a size closure, so this is bigger. The bigger I pull it back, but then this can be decomposed into union. And then you can look at this and you can renormalize by elements of gamma. Renormalizing by elements of gamma doesn't change the set. It just gives you another way of looking at it. And then the geometry will be the geometry at the boundary. And the geometry at the boundary is asymptotically totally geodesic. But I mean, you can compute it because it's strictly pseudo-convex. You make use of potential function to do it. And then it is known from work of, I think it's Umemura, that actually you don't have isometric embedding except for total geodesic. From a Kähler-Einstein manifold into the ball. I think it's Umehara. Yeah. So there's some work due to Umehara, which said, yeah, Umemura using the diastasis, which implies that the map is total geodesic. Okay. Well, then I communicated this way of approaching X-type theorems, and then with Kähler and with Zimmermann. And Zimmermann was visiting Hong Kong U, and then we discussed on how the solution for the case of a J function can be adapted to the Shimura variety situation. The case of the J functions could be solved for a number of reasons. One reason is that the normal subgroups are easy, or the algebraic subgroups are easy to describe. In general, the algebraic subgroups of G, being the holomorphism group of bounds metric domain, is huge. So it was not so easy to do it. So we make use of this approach of using foliations, looking at Charles schemes or Hilbert schemes, taking quotients and so on. And since we were working with gamma being an arithmetic lattice, there was some theory of the so-called tame geometry developed for these arithmetic groups that you can prove theorems such as saying that some set which a priori just an analytic set is actually algebraic. And this is what we can call the O minimal version of Charles theorem or Riemann-Stein theorem and so on. But it still stayed in my mind that I wanted to do it actually for arithmetic quotient, for non-arithmetic quotients at the same time. So then I continue working on it after this. Let me just translate the previous element. Yeah, so this is the translation of the Ax-Lindemann theorem, which is in terms of functions. These are the functions of Cn, these are the holomorphic functions, and it's a statement about the transcendence degree of this function field. It says that you have this inequality when the functions are restricted to a certain analytic variety, so that's an extra element of dimension B. But this statement is not going to be true if you take actually something which is contained in weakly special subvariety. So there's some difference from the transcendental number theory version. It's not universally true, it's only true conjecturally, assuming that it's not contained something totally geodesic and smaller. If you look at the way that it was formulated here, actually I learned about the formulation first from this version in a talk at ATH that somebody gave. So this is in terms of unlikely intersection. So it makes clear that one should be making use of algebraic geometry. Okay, so finally, let me say what applications one could have. The first proof of a uniform model length conjecture was given by Gao, Habecker, and Dimitrov, when they make use of the Ax-Lindemann conjecture lifted to the situation of mixed Shimura varieties. So that was based on that makes use of course, my theorem with Kähler and Zimmermann. I want to finally say that it is possible it is possible to prove I have not yet reached the point of being able to prove Ax-Chandra in general for arbitrary lattices. I restrict myself to the co-compact situation and just look at the Ax-Lindemann-Weierstrass conjecture, which for me is interesting enough geometrically. It's the question of finding the size closure of the projection under the uniformization map of an algebraic set. So I look at this. So I look at its Sarisi closure here. And the type of argument I make about rescaling still works in the case of boundary symmetric domain of higher rank. Except that if you have just finite volume condition, the analysis is much more difficult. So I restrict myself to the co-compact case. So I can do the restriction. The restriction would tell me that I can decompose. This is not the situation of ball, it's a situation like this. I can decompose this into pieces, and each piece cuts the boundary like the case of a ball. And when I do the rescaling, I would get isometric embeddings of balls. So not just one ball, but isometric embedding of one family of BNs into the manifold. The point, however, is that you cannot get very much if you just make use of the abstract argument of rescaling. You have actually to do the argument to get what are the rescaled version of it. The rescaled version of it came in Lie theory, and this has come from what are called the inverse Kähler transform. So everybody knows that the ball, the disk is equivalent to the upper half plane. Right, so this is the inverse Kähler transform. And how do you get this? You get this by pushing a point to the boundary. You push the point to the boundary. It has a certain derivative. Then you renormalize by multiplying by composing within a affine transformation, so that you get a picture like this. You get a picture like this. And in the limit, you would get the upper half plane. So the inverse Kähler transform is the limit of such transforms, which are by automorphisms composed with affine transformations. If instead of the disk you look at Bn, what you get is a Ziegel upper half plane normalization presentation. So Ziegel representation of the ball, it would give you imaginary part of W bigger than summation Zi squared. So this is what you would get. And you can do the same thing with the other boundary symmetric domain, only that it's a bit more complicated. But what is very important is that when you do this renormalization, in the case of the ball, what you get will be parallel sort of shifts of upper half planes. And what's the importance of this? When you have family of upper half planes, then you have one parallel family of translations. So this was the approach by Cindy Franco when he studied convex domains emitting compact quotients. Okay. So the point is to get translation, one parallel translation, so that you can know that this has at least some non-trivial Lie group acting on it. Now, I'm not, of course, not just looking at this domain. I'm looking at some subset inside. So I have this domain, and you have this family. And now I do the renormalization argument, and I get then a certain subset of this. What one has to do is do some estimates using intrinsic metrics that actually, after decomposing this into a family of strictly pseudo-convex manifolds and doing the renormalization, you get a family of these isometric embeddings. You know that you get them, but you have to make it precise what they are. And they turn out to be actually parallel, union of parallel families of upper half planes. So even when you do the rescaling, not for the domain, but for subvarieties, you are still able to get this, at least some positive dimensional algebraic group acting on this a priori transcendental set. And then you want to make it maximum. So, well, one very important ingredient in the proof of my theorem with Pillar and Zimmermann was to obtain normal subgroups. To obtain normal subgroups, one has to make use of the counting argument coming from Pillar, Wilkie. We don't have that. So where do we get normal subgroups? The way to get normal subgroups is to start with this one parameter group and then to maximize it. You grow it. So suppose it's not normal, then you can conjugate by gamma to get another algebraic group. and you can sort of amalgamate these algebraic subgroups together to get something bigger. So under the assumption of maximality, you still get normality, and when you have normality, the rest of the argument can go through. So let me stop here.
Are there any questions? Okay, yeah, okay, well, actually, yeah, I have one. So, can you explain a little bit more, what do you mean asymptotic geodesic? So you mean the second volume form goes to 0?
Yeah, so the norm of the second fundamental form will go to 0. It's actually going to 0, not everywhere, but at a general point. So the boundary is a circle, or an arc of a circle. So you take a disk embedded inside there. So maybe there, you don't know whether this is singular, you don't know. But at a good point, you take a sequence of points approaching it, then the norm of the second fundamental form of my Z, this isometric embedding inside the domain omega, this norm goes to 0 at the point xn as n go to infinity.
So you mean for any sequence goes to the boundary?
Any sequence. But for a general point of the boundary, there might be points where it failed, but you can take good points outside of some real analytic subset.
I see. Okay, thank you. Yeah, are there any more questions? Yeah, if not, can I ask one more? Sorry. Yeah, okay, can you go to your slide 18?
18.
All right.
Okay, you remember the number.
Yeah. Okay.
18, right?
Yeah, 18.
That's just...
Sorry, 18. All right.
Yeah. 18.
Yeah, 18.
Pseudo homogeneity.
Yeah, here, right.
Okay.
So here, okay, for your theorem, okay, so if Y only has finite volume, quotient, is your theorem still true?
We have not been able to carry that through yet. So the difficulty is because we make use of Nadeau theorem, and for that you have to make use of Kähler-Einstein matrix. Okay. And that is one difficulty. But some of the arguments went through. So for instance, the pseudo-homogeneity, because I just have to make use of Riemann extension theorem or Barnes with harmonic function, and that works in the finite volume case. So it has not been fully accomplished.
So how do you expect? You expect the answer is still true?
I still expect all statements to be true without arithmeticity and without compactness. Finite volume is good enough. That's my expectation.
Okay, thank you. Okay, so yeah, if no more questions, thanks, Professor.